Good morning, everyone. Hope you're doing okay out there and that you're keeping fit and healthy. On Show My Homework, I've put a link to the latest advice about what's going to happen with your A levels. All I would say just now is don't worry about trying to submit evidence for the time being. We're going to get some more guidance on what evidence will be accepted. And for now, I would just concentrate on getting to grips with the final chapters of your A level. And then once you're through with that, then starting to revise as you would have done if you were sitting exams in May, June. Because there's a possibility that we'll be able to set you some kind of a final mock to update our predicted grades. And the other thing that is possible, or seems to be an option, is that if you weren't happy with your predicted grade, you would be able to do an exam as soon as possible once schools are back open. So for now, just concentrate on finishing the current units and getting ready for any exam which might happen in the future. Okay, so moving on to the new unit. So the final unit for us on the A level is going to be Unit 18, which is looking at further hypothesis testing. So what better way to start than to look back at what we did last year, which was hypothesis testing with the binomial distribution. So I'm going to give you a moment, and you might want to pause the video here to have a go at the question in front of you. Okay, cool. So hopefully you paused, had a shot at that question. So the question was asking us to look at a discrete random variable, which had a binomial distribution with n equal to 20 and p equal to 0.41. And initially you were asked to find the probability that x was between 3 and 7. And then question B asks you to test at the 5% significance level whether the proportion of customers ordering a starter had decreased. And then you had to state a conclusion if you were testing at the 10% significance level. So hopefully what you got on your calculator for part A was 0.368. And then for the second part, you had to set a null hypothesis. So that's the status quo option, that the probability is equal to 0.3. And then you had to set an alternative hypothesis that the probability was less than 0.3. And because we're looking at the 5% significance level, you then look at, well, how likely is it, given that distribution, that we get an x value that is less than or equal to 7. So if that's our distribution with p equal to 0.3, how plausible is it to get that result? And because because the likelihood of getting that result is bigger than 5%, then we say there is evidence to accept the null hypothesis. So we stick with the status quo option. If, however, we were testing at the 10% significance level, then because 0.0553 is less than 10%, we would say, and I'll be careful with saying that we would accept the alternative hypothesis. I wouldn't use that language. Instead, what I would say is that there is evidence at the 10% significance level to reject the null hypothesis. Okay. So that's just a recap on using the binomial distribution and hypothesis testing under the binomial distribution. So that's what we did last year. Last year we were thinking about testing the assumed probability in a binomial distribution. So assuming we have a particular probability of an outcome, and then given the results of some sort of experiment, trying to establish how likely it is that that originally assumed probability is the case. In this chapter, what we're going to move on to look at is how we can use hypothesis testing to test an assumed mean in a normal distribution, and also to test the link between correlation in a sample set of data and its relationship to the whole population. Okay, so we're going to look at this in steps, and this first video is just looking at section 1, which is thinking about the distribution of the sample mean. Okay, so let's imagine we've got a continuous random variable x, which has a normal distribution with mean mu and variance sigma squared. So, for example, let's say this was the mass of a female gerbil, and we're saying that the mass of a female gerbil is normally distributed with mean mu and variance sigma squared. And you can see the the probability density function that's been sketched down here. Okay, so if we take one female gerbil, the most likely outcome is that she will have a mass equal to mu, and then it becomes steadily less likely that she will have a mass that is less than mu, and then similarly steadily less likely that she'll have a mass bigger than mu. Okay, so if we take one gerbil in this normally distributed continuous random variable, if we take just one gerbil, then the most likely outcome is that we will get a gerbil of mass mu, but there's still very likely outcomes which spread out around that mean mass from within certain numbers of standard deviation. So yeah, so just what we said before, so 68% of the data will lie within one standard deviation, 95% of the data will lie within two standard deviations, and 99.7% of the possibilities will lie between 3 standard deviations. Okay, so what we're interested in now is, instead of just taking one gerbil and thinking about the possibilities around that one gerbil, we're actually going to sample a group of gerbils, and we're going to think about, if we sample a group of gerbils from our population and then take the mean of those gerbils, what does that data look like? Okay, so we use this notation x bar n, although usually it's just written as x bar, and that's saying that we can create a new random variable which is equivalent to the sample mean. Okay, so if we take groups of, let's say, groups of 4 randomly selected gerbils from our population, then we can find the mean for each of those groups of 4 gerbils, and then we create a new random variable, which is x bar. In this case, it would be x bar 4, and that turns out to be normally distributed with a mean that is equal to the mean of the full population, and a variance which is equal to sigma squared divided by n. Sorry, let me just put that in there. Okay, so now we're taking samples of the data, and we're finding the mean of those samples, and then we're putting those sample means into a distribution, and it turns out that the distribution of those sample means is also normally distributed. Okay, so you can see, if we take there's some examples here. So if we take sample size of 2, so we're going to take lots of samples of 2 gerbils and find the mean weight mass of those 2 gerbils, you can see that our outcomes form a normally distributed function. Okay, if we take samples of 4 gerbils at a time and we find the means of those sets of 4 gerbils, they form a normal distribution as well, and so on. Yeah, if we could take a bigger sample size, so if we take sample size of 8 and we find the mean of those 8 gerbils each time, again, the sample means form a normal distribution. And in each case, the mean of those sample means, so the most likely outcome for the mean, is going to be the mean of the original distribution. All right. So the most likely outcome is that when you take those groups of 4 or groups of 8 or groups of 2, the most likely outcome is going to be that the sample mean is equal to the mean of the whole population. And basically, as we increase, so let me just bring up this, as we increase the sample size, what you can start to see, in our diagram here is that the variance from the mean is reducing as we increase the sample size. Okay, so if we're finding the mean of bigger sized samples, it becomes increasingly likely that the mean of that sample is going to be the mean of the whole population. So let me just show you that in this little diagram. So we're going to start off, right, with taking, let's make my, so I've got, this is our gerbil. So we've got the mass of female gerbils is normally distributed with a mean of 8 and a standard deviation of 0.1. Okay, if we just choose one gerbil from our population of gerbils, then obviously the chances of the likelihood of getting a particular value is going to be the same as the normal distribution. So the most likely outcome is that we get a mean of 8 and then the means span out from there. We're only dealing with one outcome, so it just follows the original normal distribution. If now, however, we think about taking sets of 2 gerbils, so we're taking 2 gerbils out of the population, we're finding the mean of those gerbils, and then we're putting that x bar, that mean, the sample mean, into a distribution. We can see we've still got a normal distribution. The variance has started to come in a bit. Okay, so the variance of the mean sample means from the population mean is reduced. And again, the most likely outcome is that the sample mean. So if we take 2 gerbils and find the mean of the mass of those gerbils, the most likely outcome for that sample mean is that it's equal to the mean of the whole population. And as we ramp up the sample size, you can see that the variance from the mean, so what that means is taking a group of 8 gerbils and finding the mean mass of those gerbils. Again, the most likely outcome is that the mean mass of our sets of 8 is equal to the mean of the population, but we still have this possibility to get a mean for our 8 gerbils that is less than or more than the mean of the population. And ultimately, if we increase our sample size dramatically, then it becomes almost inevitable, and hopefully that makes sense, it becomes almost inevitable that the mean of the sample is going to be the same as the mean of the population. Yeah, so the overwhelming outcome is that if you take 100 gerbils and find their mean, in almost every case the mean is going to be equal to the mean of the population, but again there's still some variance either side. And if we take that sample size up to 100,000 gerbils, so that means taking 100,000 gerbils and finding the mean mass of those gerbils. We do have a normal distribution, but now the variance is almost 0. And so in almost every case where we take a sample of 100,000 gerbils, we'll get a mean, sample mean, an x bar, that is equal to the mean of the originally normally distributed variable. So the mean of the whole population. I hope that makes sense. So what you're and mathematically, why it makes sense is because the where we take a sample mean and we think about the distribution of the sample mean, we say that it is normally distributed, with a mean mu. So no matter what sample size we take, the most likely outcome is that the mean of our sample size, the sample mean, is going to be the same as the mean of the whole population. And the variance, meanwhile, is equal to the variance of the whole population, sigma squared, divided by n. So obviously, as we make n bigger and bigger and bigger and bigger and bigger, this value, the variance of the sample mean, is going to get closer and closer to 0, which is why we see the graph starting to spike up through the middle. Okay, so we don't need to know the proof of this relationship, but we do need to know that if we have a normally distributed variable x with mean mu and variance sigma squared, then the distribution of the sample means of the data is also going to be normally distributed with a mean mu, but with the variance of sigma squared divided by n. If you want more detail on this, or you want to see how we then go on to use that in calculations, you can watch this good video, sample distribution of the sample mean. And then for now, if you take a break and then come back and try exercise 18A. Okay, good luck with that. If you have any problems at all, make sure you email me, and yeah, I'll speak to you all soon. Take care. Thank you. Bye.